Okay, we're going to go through all the core concepts of system design so that when we actually start learning about event-driven systems, which is a very difficult concept according to many people. It's a challenging engineering concept, and understanding that will supercharge your career. So to understand that, you need to understand system design really well, beforehand. So what we'll do is we'll go through this presentation for about 45 minutes. We'll go through system design basics, and whatever you learn right now in this presentation, you have to then I'll take some quizzes, and then you have to answer all those questions correctly. Then we'll take a quick break, and then we'll learn about event-driven systems. Like I said, this is a complex topic. It's an event, it's a difficult topic, so we'll learn about that in detail. Then we'll actually design the system design, or we'll go through the system design because I've already designed or drawn the system design for you guys, so we'll go through it together. Then the last 15-20 minutes we'll spend on Q&A. So it's a 3-hour session. Usually it ends around 2 hours, 50 minutes, 2 hours, 45 minutes, and sometimes it goes to 3 hours depending on how we go. We won't go very fast. We'll go at a comfortable pace, not very slow, not very fast. So let's do that. So what is system design, right? So there are many of you who have like no idea about system design, like no context, right? So all the senior guys who have more than 10 years of experience, for the first 40 minutes, I request you guys to be a little patient, because we need to get all the people who don't have experience with system design. We want them to get them up to speed, so that everybody's on the same page and we all can understand what's going on in the session. Otherwise, it can be a difficult session otherwise. Okay, so system designing is basically a planning exercise. So what usually happens is, let's say when you have to build a product for a particular scale, what you do is you do a system design planning exercise, and then maybe you'll do some cloud architecting exercise, in the sense you'll decide. So with system design, you plan as to which technologies you'll use, in the sense, will you be using a load balancer? Will you be using what type of databases you'll be using? Not the name of the database, but what type, in the sense, will it be an SQL database, no SQL database? What type of architecture generally would you be choosing? So all of those are system design problems. Cloud architecture problems are problems where you have the system design ready. You have to use a load balancer. You have to use a NoSQL database. You have to use a streaming platform. But what are the exact technologies that you'll use on which cloud provider's platform? That's the problem for the cloud architect. Okay, so system design usually happens before everything. So usually when you have very less amount of experience with engineering, you start writing code directly, right? So that's a wrong practice. You shouldn't start writing code directly, because there will be places where you'll head into bottlenecks, you'll hit roadblocks, your app will stop scaling. So instead of going through all that problem, if you spend some time in planning and designing a proper system, and preempting all those problems, you won't have most of those problems. So the first thing you do is system design, then you do cloud architecture, then you do software architecture, where you think about which pattern to use, which design pattern to use, and all of those, right? And then you think about the project structure. How will you have like a models folder, or a controllers folder, or a routes folder, all of that, and then you start writing the code, right? All of these things happen before you start writing the code. Some of you who don't have much experience, you might be just writing the code directly as soon as you get the requirements from the client, or from the business analyst, or from the product manager, product owner, whoever it may be, or maybe just directly from your CEO or whatever, depending on what size of company you're in. Maybe you're writing code directly, but when you move up the engineering ladder, this is the right process that is usually followed to get a better product, right? So what's the significance of system design? Why? What is it exactly, and what's the significance? So system design is basically a macro level view. It's you're looking at the system or the complete product from a 10,000 feet perspective. So you need to have complete end-to-end product tech understanding. So like, let's say when you start out as an engineer, you don't have much experience, and you just work on either a function or a file or just a microservice. That's all you work on. You don't have the entire visibility or clarity on exactly what technologies are being used in the entire architecture of the product. So only when you have end-to-end product understanding would you become a good system designer. Okay, will you become good at system design? And it's important for leadership. Now, somebody who just knows about a particular function or a particular language or just a file or a microservice, that person is not fit for leadership position, like a CTO or an engineering director kind of guy. He needs to understand the entire product from end to end, right? So you need systems thinking, and you need to get a complete overview of the entire product. So that's the significance of system design. What's the skill set? You need to have a problem solving mindset and a skill set. So the better you get at DSA, it kind of helps you with, but the better you get at problem solving in general, the better you get at system designs as well. And you need to have at least a working conceptual understanding of all the technologies being used in your entire stack. So when the products, they evolve, like in today's session, we'll be taking the example of Robinhood app, which you use to trade stocks. So when a product like that, it evolves, right, over a period of time, there are a lot of complexities added into it. And usually when this particular session, like I said, gets repeated, it also gets repeated in the US many times. So there, the engineering managers from Robinhood or the technical architects from Robinhood, they also join in these kind of sessions just to understand what's happening, or just to get a better view. I mean, obviously they're not there to learn in the session, they're just here to check if what I'm teaching is correct. So I keep getting a lot of feedback. So all of the content that you'll get here, it's been refined from a lot of sessions before, and a lot of people who have already joined, they've given me a lot of feedback. So the skill set that you require is basically you need conceptual understanding of the entire tech stack, okay? And you need planning skills and preemption skills. So you need really good planning skills, which at the beginning of your career, you don't have good planning skills, right? You start writing code directly, and then when the problems happen, then you react. That's not how it works with system design. System design, you preempt those problems. They should not happen and then you react. You always need to be 2 steps ahead of the problem. You've always expected the problem to happen. You've already found the solution to it, and you have already implemented the solution to it, okay? You're already always ahead of the problem before they occur. And that's called as good planning, generally, right? With system design, you're basically thinking of systems that can scale beyond a particular amount, okay, beyond a particular capacity. If you just have to make a very simple website, you don't need system design for that. You only need system design when you have to work with millions of users, because many problems can occur, right? Many problems can occur when there's a huge scale and they're using the product every single day, let's say multiple times a day, like something like Robinhood, where you used to, you use Robinhood to buy and sell stocks. So systems like those, which are used every day, they need to scale a lot, right? Now, system design, if you really want to understand system design, right, you have to understand that it's inspired from the real world. In the sense, in the real world, like for example, let's take the example of parking lots. Now, when you look at a parking lot, you see that there are multiple entry points. If there was only one entry point, the whole parking lot will get choked, right? It doesn't matter if your parking lot has thousands of places to park. If it just has one entry point, it will get choked. That'll become a bottleneck very fast. It won't scale up. So you have to think about scale. You have to think about bottlenecks, right? Think of restaurants. Even restaurants have multiple chefs, and they have repeatable recipes. So even if one chef is not working today, or one chef leaves the restaurant, there are other chefs who can use the same recipe and repeat it and get the same result. So restaurants have multiple chefs, they have repeatable recipes, right? Then you have gas distribution pipelines, which have multiple vents, knobs, checkpoints, and parallel pipelines, all of those things, which help you with failure discovery and failure recovery, both of these. So in the real world, people who design things like parking lots or restaurants or gas distribution pipelines, they are really good at system design. And this is where system design has come in from. It was later adapted to the software world. It's very similar to how the lean principles, they were born in the Toyota car production factories, like the lean principles. Now they have been applied to the software world. Similarly, system design is the same thing. You want to think about scale, you want to think about the bottlenecks that can appear, think about failures and recovery. Now, this is also the reason that in many of the junior level system design problems, like let's say you have 2 or 3 years of experience and you're going to a system design interview, the kind of problems you'll see will be very simple. They'll look very simple. They'll be like design a parking lot, or design a restaurant, or design a gas distribution pipeline. They'll be like this. They'll be like real world problems they'll give you, right? They won't give you an advanced problem like today we have the stock market trading platform. Okay, so today we are looking at the system design of stock trading platforms. This session is for engineers only. Okay, this is not relevant for UI UX designers. Sometimes what happens is that when they look at the session, let's say system design, so they think that it's a design session, but if you're a UI UX designer, you won't understand anything in the session. It's not relevant to you. You're just wasting your time. It's not relevant for stock traders also. Somehow when we say stock trading platforms, a lot of stock traders, they end up attending the session. They think that's for them. It's not at all. You won't understand anything that's happening here. It's about how to think of the system design for stock trading platforms. Nothing to do with design, nothing to do with stock traders. It's even for product managers, this session will be very difficult because the system design that's expected of product managers is at a very basic level. This is for hardcore engineering technical stuff today. So just wanted to get that out of the, want to get that out. So there's no coding involved today. We're not doing any coding. We're going to understand the system, how to design a system, not to actually do any actual coding. Like I said, there are 5 steps that need to happen after you start coding. So there's no coding there today, and it's an advanced level problem, right? So like I said, the basic level problems will be like design a parking system, design a restaurant, design a gas distribution pipeline, and then we'll have some intermediate problems like designing a social media platform, navigation systems, and like a ride-sharing applications. All of those are intermediate problems. Then you have advanced level problems. So a stock trading platform problem, only if you have more than 10 years of experience, only then you can expect this kind of a problem in your interview. Otherwise, you won't see this kind of a problem in your interviews, right? So you have to understand that today, whatever you're learning will be advanced. Okay, there'll be a lot of knowledge that I'll share, and it'll be very relevant to you if you have more than 10 years of experience. But even if you don't have any experience, if you have like 0 years of experience, I'll go over everything very slowly and we'll build upon each concept so that even if you have no experience, you'll understand a lot in this session. You won't go empty-handed, okay? But you also have to understand the complexity of the topic that we're dealing with. Okay, it's not an easy topic. It is the most advanced system design problem that you might see in a system design interview, because it works with real-time systems, works with event-driven systems. We'll be using microservices. So we'll do a lot basically today, okay? So a prior system design knowledge will be helpful, but if you don't have any context about system design, don't worry. This presentation will take you through the basics of system design and you'll understand everything, okay? And today we're working with only high-level system design. There are 2 types of system design, high-level and low-level. So let's look at the difference between these 2 so that you have some clarity. Now, in high-level system design, we'll be looking at tech components only. In the sense, let's say we'll just talk about the stream, using a stream or a queue or a load balancer. We won't talk about the actual technologies. For example, we won't say that the queue that the stream that you'll use will be a Kafka or a Spark stream. We won't say the database that we'll use, the NoSQL database that we'll use will be a MongoDB or a Cassandra. We won't really take the names of them. We don't have to in an HLD round. In LD rounds, you may need to talk about those common components in depth. So when you walk into a system design interview, you might want to clarify, do you want me to design an HLD or an LLD, okay? High level or low level. Like I said, exact technology is not discussed, and you don't have to go into the DSA with HLD. There's no requirement for DSA. They're not expecting DSA from you at all, because before an HLD round, your DSA round has already happened. Right? There are 3 rounds, right? The first interview round, then or the coding round, then you'll have the DSA round, and then you'll have the HLD round. HLD round is always the last round. Now, one more pointer is that as you go up in your career, high-level design will start taking more and more importance in your career, and DSA will start taking less and less importance. So, because if you have more than 10 years of experience, 10, 12 years, the interviewer already knows that you've done every single problem out there that's on lead code or whatever, right? You've done all the problems out there. You're very good at DSA. And they already have a separate round for DSA. And sometimes they even skip DSA rounds. The people who are applying for engineering, tech architects or CTO positions, probably there's no DSA or coding rounds. There's just system design. Okay, so you have to understand that the higher you go up in your career, HLD takes more and more importance. The better you get at HLD, the higher your probability of getting a position like a CTO in a good company. Okay, so with HLD, you don't have to do any API or JSON design. With LLD, you might need to do some schema design. You might need to do some API design, right? So LLD is about schema, API, underlying DSA. You want to talk about all that. HLD, you don't want to. Okay, I hope that's clear. So having gotten all of that out of the way, now we will go through all of the most important system design concepts that you must know before you do any system design problem. Okay, so these are very critical. You will be getting all of these presentations, whatever I share today on my screen, whatever you'll see, this or there'll be a board where we'll go through. You'll get everything after the session. Okay, you'll get everything in that WhatsApp group that Scalar has created for you guys. So don't worry about it. You'll get everything. Okay. So now we're just going through all the system design concepts very fast so that all of you are at the same level when we actually start talking about real-time systems and microservices, all of that stuff. You don't get confused. Okay. So what are load balancers? So when you start building a more complex website where you have to serve a lot of traffic, right? There's a lot of traffic that's going to come to your servers. You don't want to use just one server. You want to have multiple servers. When you have multiple servers, you need a special program or special software which helps to decide which server gets how much traffic. Depending on which server is down, which server is overloaded, the load balancer decides which server gets what traffic, basically. That's all it does. Okay, so that is load balancer. Now, load balancer itself is a huge concept, right? There could be a 3-hour session on just load balancers, and every single slide that I'll go through is a huge topic in itself. But to keep things simple, I'm just going to define them in just one line so that you have the basic, absolute, bare bones idea about what these topics are, and you at least have an understanding and an intuition about these, so that even if you want to learn about them, you can go deeper and you'll have a very clear understanding. Okay. Caching. Now, when you are making a request to a database, let's say, or a server, you don't want to keep calling the database again and again. At least too many requests, it can slow you down, it induces latency. Latency is basically going to slow things down, right? And these operations are expensive. If you're using a database like DynamoDB, these operations can be quite expensive, right? In terms of time, in terms of money, both. So what you want to do is you want to store the most often used information. You're going to store that in a cache. So here I've taken the example of a Redis cache. So you store that information in a cache. Instead of getting it from the database all the time, again and again, you get it from the Redis cache. Now, caches are faster because they're smaller. They're in-memory storages, so you can access them faster, and they basically save time and money both. Now, the problem is that a lot of people, when I show them the concept of caching, they think that, oh, but caching can end up becoming a point of failure for the project, right, for the software. But that's not the case, because caching, whenever you cache something, you'll always have it in a distributed manner. You'll have distributed caching. Distributed basically means you have multiple replicas of the cache. Even if one cache goes down, there are other caches to help serve the servers or the database. Okay. Usually, in the real world, this is what the cache will actually look like. It'll be a cluster. There will be multiple clusters. Each cluster will have its own multiple nodes. Each node will have multiple replicas of the cache. And this is what the Redis class cluster will look like. So even if one of the replicas goes down, the whole node is there. The entire node goes down, the whole cluster is there. The whole cluster goes down, there's another cluster to take the entire load, right? So it can keep serving all this information. So make sure you understand that caching, or any of the concepts that we learn about today, we're not looking at them in isolation, right? Even load balancers or any of the concepts that we learn today, we are not thinking about them in isolation. We're always thinking that there will be a cluster, or there will be like a distributed way in which these caches, load balancers, all of these things will be active. Okay, I hope that's clear. So there are three types, three places where you can use the cache: database, front end, and backend. So in case your front end server makes a lot of requests to the backend server, put a cache here so that the front end doesn't have to always call the backend, or takes the information from the cache. Backend server does not have to always make a request to the database. It can always make a request to the cache instead. So that's the three places you can use the cache. Now comes scalability. So we are in a session by Scalar. Scalar, where you think about scale of products, right? So scalability is something that you have to think about when you're designing a system. That's the most core important funda, right? So scalability has 3 axes: latency, throughput, and capacity. So latency is when you make a request to a server, the response that you get, the delay before you get the response is the latency. So the more the latency, that means the more it's taking, the more time it's taking to respond to you. The less the latency, that means that responses are very quick. So you want less latency. Okay, people confuse this a lot. They think that they want high latency. No, you want low latency because you want as less delay as possible between your responses. You need to have a high throughput. That's basically how much data can pass through the system at any given point of time. So like it's like Mbps or Gbps, PBPS, right? How much amount of data can pass at a given point of time, like per second or per minute or per hour. Now, capacity is not bounded by time. There's no per second or per minute. It's an entirety how much data can be stored or how much data can flow through the system in entirety. Okay. Now, what's important to remember is performance is not equal to scalability. Okay. Performance, basically, you can have very low latency and your system can be highly performant. But if it doesn't have the capacity or the throughput, it won't be scalable. So people confuse these two concepts a lot. And in the chat, also, you'll see a lot of people asking me this question, same question. Every session, I get the same question. Hey, what's the trade-off between performance and scalability? Are they the same? Like many questions around that. And even interviewers, they ask you many questions around this. You have to understand performance is a completely different concept. Scalability is a completely different concept. Okay? And these three things are like capacity, throughput, and latency are the three axes of scalability. So scalability, a little bit more about scalability. You have horizontal and vertical scalability. Horizontal basically means you add more servers. So I'll just give you an example actually instead of going into the jargon of things. Let's say you have an AWS account. You create one EC2 instance and you start getting some traffic on your website. Now you want to ensure that your entire system does not go down. What do? You start creating one more EC2 server, and you basically connect all of them to the entire network, and you say, okay, I have all these different EC2 servers, so that even if one becomes overloaded, there are more to take up the load. So that's basically horizontal scaling. You keep adding more and more EC2 servers. Vertical scaling is basically, let's say I have an EC2 server, it's a T2 micro server, and I made a T2 medium, T2 large, whatever I keep making it, like I keep increasing the size of the server, I'm scaling it vertically. Okay, so that's vertical scaling. So you have two types of scaling. Now, to horizontal scaling, so between horizontal and vertical scaling, horizontal is usually the good type of scaling. It's more, it's better, it leads to better results. But there are two laws that get applied to horizontal scaling. One is the Amdahl's law, the other is the universal scalability law. I will quickly explain these to you. These are slightly difficult concepts to understand, but they're also very important. So I always go through these because they can be very important interview questions, and I don't want you to miss out on interview questions, right? That's why you're probably learning all this for. And now, again, this is not just important for the interviews, but it's also important to understand how systems work in the real world. So Amdahl's law is saying, this, by the way, you'll have this presentation after the session, so you can zoom in also and see it properly. But what Amdahl's law is saying that you keep adding these servers, right? So I have these number of processors that keep increasing. They keep becoming double. I will get a speed up in my system. So I will get 2x, 4x, 6x, 10x speed. The system will start getting a lot of speed. But it will all max out at 20x. So more than 20x speed, I get something called as the law of diminishing returns. In the sense, the speed of the system does not increase after that. And even if I add 1,000, 2,000, 4,000, 8,000 servers after that, the speed stops increasing. So this is what happens in the real world. In the real world, you can't keep scaling unlimitedly and keep getting a lot of speed. You have to have, at 20x, the amount of speed up that you get, the system stops, and then you stop getting any results. Now, universal scalability law says that that it doesn't even happen till 20x. So there was the Amdahl's law, then came the Gunther's universal scalability law. He says that even 20x you won't get. You'll just get somewhere around 10x, 12x. So here, this line that you see here, the blue line, that's saying that around 12x, you'll start capping out. You won't get any more speed up above 12x. This was the ideal. It keeps increasing. But this is the actual speed up, the blue one. So why does it happen? It happens because there is something called as a communication constraint and the latency constraints that get added to the Amdahl's law in the real world, which make it, which make the speed up impossible after 12x. So that's important to understand, because when you're working with so many servers, you get communication constraints. You can't like communicate with all the servers at the same time. You have to use load balancers, and latency is induced because they have to communicate with each other. So all of that happens, so you don't really get more than a 12x scaling. Okay. Then you can scale with the help of distribution. So you can distribute data in the sense from your application, you store the data in 3 different databases. Or you can distribute compute. You can use 4 different servers to compute the information by dividing them into small parts. Or you can replicate data. So there's a main data store, which is your main database. It creates 2 small replicas so that even if the main database goes down, one of the 2 replicas becomes the main database. So they're all communicating with each other, and then one of the databases, the replicas, becomes the main data store. So with state, how do you scale with state? There are 2 ways. One is the stateful way of scaling, stateless way of scaling. So stateful server. So when we used to use PHP long back, right? Technologies like PHP, we had state-based servers. So in the sense, you were storing the session information on the server side. The problem is that for the client A being the front-end server or just the client A is making a request to server 1, and server 1 has the data for client A. So if server 1 goes down, client A cannot ask server 2 for the information because only server 1 has the session information for client A. And that's the problem, right? So if client B goes down, client B cannot ask server 1 or server 2 for any information because only server 2 had that information. So that's the problem. Where with stateless systems, you have multiple servers, and all of these servers don't store any session information. All the information is only stored in the databases. So you can use load balancers here, and they can simply redirect the traffic to any of these servers. Now, even if one server goes down, because the servers were not storing any session information anyways, even if one of the servers goes down, the load balancer can send the request from the client to any of the servers, and it'll all work perfectly and smoothly. So stateless systems are better, and in modern system design, we always use stateless. So you just want to understand that modern systems are all about stateless, and we'll be using that in today's system design. This can be a big interview question. Which one scales better, or what is state, all of that stuff. Now you know the answers. Okay, so important topic, sharding. Your databases cannot keep endlessly storing information because they start failing, right? They start going down. You've seen databases getting overloaded, all those problems. So how do you scale databases? You scale them by sharding them. So you create either vertical shards or horizontal shards. Vertical shards, what you do is you divide the columns into different databases. With horizontal shards, you divide the rows in different databases. So here's the original table. The first vertical shard will have first name, last name. Second vertical shard will have the city. So you've divided from the columns. You've divided into 2 different databases. So now it becomes easier to store information. And similarly, you can keep dividing into more and more shards. With horizontal shards, you can store between, let's say, the first 2 rows you store in the first database, and the second 2 rows you store in the second database. Now, obviously, this is an example, right? So many people, they don't understand that I'm just taking an example. So they ask me a question in the chat saying, hey, for 4, this is such a small database, why do you need to do any sharding? I'm just showing you with a small example. This is a small database, but in reality, you would have like thousands and thousands, millions of records probably. That's where you do horizontal sharding, and you'll have thousands of columns. That's where you'll do vertical sharding, right? I'm just showing you using a small example how it actually works. Database is replication. So you have the original database, and it stores information in replicas. Okay, so even if the original database goes down, one of the replicas can actually become the original database. Now the problem here that you need to know that replication sounds like a really good silver bullet. It can solve everything, but it's not the case. You need to know the problems or the cons behind replication of databases. The problem is that it can lead to inconsistency in the system. So whenever there's some new information that gets written from the server to the original database, that needs to traverse through all of the replicas, and all of them need to have like a consensus that this is the new information. So all of them get updated. But if there's some new information in the original database, and before it's able to write information to them, it goes down, it crashes. Right? There's an attack on this database. Then that information is lost. And one of the replicas, who now has to become the original database, the main database, will not have that recently written information. And that's when the entire system becomes inconsistent with each other. And that's the problem. So that's the problem with replication. You need to know that inconsistency can occur in the system. So with systems where consistency is of critical importance, like payment, right? You don't want to have multiple payments, or if payment has gone through, you didn't store it in the database. That's a big problem, right? Payments. You might want to refrain from using too much replication, or you might want to have different strategies. Okay. Indexing of databases. So let's say you have a table which has ID, name, and city, and you had sorted by ID, which is auto increment IDs, stored by IDs. And you have name and cities. Now, what if you wanted to be able to search much easier from the table? What if you wanted to be able to search in a better way? What you could do is you could put an index on name. On the name field, you put an index. That means that the data will be organized based on names. So like Andrew, Blake, Dave. So from A to Z, we have organized it. Now what happens is that when you have, let's say, 10,000 records, right? And you put an index on the name. Now you know whenever you search for, let's say, Zach, this guy called Zach, our system knows that there's an index based on name. So if there are 10,000 records, the first 9,000 records it does not have to search. It just needs to search the last 1,000 records, or maybe even the last 500 records. That's it. So that's the beauty of using indexes. Otherwise, you would have to go through the entire database, all the 10,000 records, and that will be very slow. This is why indexing makes searching for data faster. So indexed based on the name. SQL versus NoSQL. So with SQL, you have RDBMS systems. We all know what are SQL databases. NoSQL, there are multiple types of NoSQL databases. You have key value stores, you have graph DBs, you have document DBs, and you have column DBs, column stores. Okay. NoSQL databases are horizontally scalable. So like MongoDB, right? You don't have to have a strict schema. Even if there's a schema-less information, completely okay. You don't have to do any painful migrations. In our case, a NoSQL database is going to be really good. We're going to have a microservices system where we'll have like multiple databases, different types of databases with different microservices, but mostly we'll be relying on NoSQL databases because the information that you get from each stock, it keeps changing. That the same number of fields are not there for all stocks. So we want to have something that can work with a very flexible or dynamic schema. So we'll be using NoSQL databases mostly. Row DBs versus column DBs. So row databases, you store a lot of rows, few rows in the databases. But in the column databases, you store, let's say, the ID column in a database or name column in another database, and so on. Store based on columns. Column databases. So in our system, right, there'll be a service for stock data. So we'll be having like stock related information. And this is usually a read-heavy information. So users are always reading this information, stock-related information. And this is usually a read-heavy system. So for read-heavy systems, you are better off using column stores. Or any other use case, like let's say analytical or analytics engines, creating data visualization, all of that. Column data is really, really good. So column databases are like Cassandra. They're a very good fit out here. Proxies. So you have forward proxies and you have reverse proxies. Proxies, basically, if you're exposing your servers to the internet, you want to hide the IP addresses and the location of your actual servers. So for example, if you have clients who are going to, make a request to your front-end servers, the location of your front-end servers can be hidden with the help of a forward proxy. Whereas if you have your front-end servers and your other external systems integrated with your servers, you can have a reverse proxy to hide the IP addresses of the backend servers. If the external systems, like external integrated systems, they come to know the location of or the IP addresses of your servers, they are going to attack it and get your systems to go down or steal all the information. You don't want that. So this is why you use proxies. Okay. Then you have rate limiters. Now, when you have systems like stock trading platforms, a lot of bots, trading bots, they end up using the platform as well. So I'm sure all of you who are Python developers, you've already probably built your own stock trading bot in the past. When you use these kind of bots, or maybe scraping bots, right? You scrape all this information. A lot of competitors, right? They scrape information from others' platforms. So this happens a lot, at least in crypto platforms. So what happens is that you have a crypto exchange. The other crypto exchange has some, like, is trading at different values, and you're trading at different values. The customers are going to go to the place where there are the stocks are cheaper, the cryptocurrencies are cheaper. So you want to keep always scraping their information, because they're obviously not going to share their APIs with you ever. So you have to integrate, you have to keep scraping their platforms just to be updated with the latest information on their websites. So like I said, there are a lot of bots or a lot of external APIs who may be integrated with you guys who are making too many requests to your server. Or somebody who's trying to use like a Hydra or something to make too many login attempts, like Medusa or something, to make too many login attempts to try to log in, and he's getting failed login attempts. So you want to have a system which says, hey, you from your IP address, you as a user, you've tried too many times. I can't allow you to try this any more time, because you've exhausted your rate. That's called as rate limiters. If you don't have rate limiters, your entire system can be brought down. Like I said, your system can be overloaded with just a few users who can make too many requests in just 1 second. With technologies like Golang, you can parallelize, you can run so many processes in parallel, and you can all of them make a very fast attack on a website, and you can bring them down. So this is why you need rate limiters. The most important concept in system design is CAP theorem. CAP theorem basically says that you can't have all three, which is CAP, all three together. So C is consistency, A is availability, P is partition tolerance. If any of you guys are from the blockchain background, you probably know about the blockchain trilemma, where you know that all three things cannot exist at the same time. So here in Web 2 world also you have the CAP problem, where so let me go through all the concepts together. So consistency basically means, let's say there are two databases, they are consistently talking to each other, and the two databases, if you make a request to both the databases and they give you back the same information, because they were in communication, right? They were in communication with each other. So when you make a request to them, they give you back the same information, that was the recently written information. And the information is the same from both the databases. That means both the databases or the entire system is consistent. Available basically means if you make a request to the database, it responds back in a given amount of time, like let's say 1 second or 2 seconds. The system is available. That's availability. It returns back data in a given amount of time. Partition tolerance basically means, let's take the example again of those two databases. They were in communication with each other. And if the communication breaks down between the two databases and you still make a request to them, they still give you back the same information, the recently written information, which is consistent. That means the databases or the system is partition tolerant. In the sense, even if the communication has broken down between them, they return the same information. They're both they're partition tolerant. So you've understood consistency, availability, and partition tolerance, but you also need to understand that all three CAP cannot exist together. You can't have all three together. So you always have to prioritize. Now there's a hack. The hack is that with microservices, you can decide which microservice can get what priority. You can either have CA or CP or AP, depending on each microservice. Or otherwise, if you don't use microservices, for the entire system, you have to pick one, CA, CP, or AP, one of these three. And only that you'll have to prioritize for the whole system. Okay, so let me give you an example just to make it clearer. Availability, basically like Facebook or Instagram, you always go there, you always want to see it live. You don't want the website to be down ever. Or Amazon.com, they need high amount of availability. Anything that has a lot of payment related information, right? You're making some transactions. Availability is not important. Consistency is very important, because even if the system is down, it says payment failed, sorry, servers are down, like Google Pay tells you servers are down. That is acceptable to you. But if money goes twice or thrice, you will panic, right? So consistency is more important than availability there. Whereas on Instagram, if the same post gets shown to you twice, you don't care. Right? Availability is more important, not consistency. So you have to pick and choose based on your system. And we'll do that. We'll also pick and choose based on our system when we actually start going through the board. So microservices, you have, when you start out with any product, you usually have it as a monolith, in the sense you have a UI layer, you have a business logic, and you have a data access layer. It exists in one big chunk called the monolith. And microservices, basically, you start dividing those monoliths into very small chunks called microservices, where you start dividing the business logic into different parts. It makes it much easier to handle, much more easier to work with, and a great pattern is to give a separate database to each microservice. API gateways. Now, when you're using the microservice pattern, you don't want your front end to go and find or go and do the work of finding which service has what data. So you want to use something called as an API gateway, which is like the single entry point for all the APIs, or the single entry point for the front end to interact with any of the APIs. So it's the API gateway's problem to find out which server or which microservice has what data. The front end just needs to make a request to the API gateway. Otherwise, the front end would become really overloaded. So it's a single point of entry for the client. Now, API gateways don't exist in isolation. Many times, what you'll do is, this is an important point, guys. If you're not paying attention, please just listen to this one sentence very carefully. That many times in API gateways, you might be seeing that API gateways already have a rate limiter and proxy already implemented. Sometimes even load balancers are implemented inside the API gateway itself, right? So load balancers, rate limiters, proxies, all these three can actually be implemented inside the API gateway. But in mostly, like 99% of the systems, you'll see that there's a separate load balancer. And you'll see that rate limiters and proxies might be in API gateway, but load balancer is always separate. Okay, so this is at least what I've seen in most of the systems. Even in the later systems, this is how it happens. People have started using rate limiters and proxies, and they've started rolling that up into an API gateway, just to make things more efficient. API composers. Now, when we have like multiple microservices, a lot of data exists in different services. So you have like authentication information or user information somewhere else, and what the user traded, all his trades in some other place, and you want all of that information together. And since which user did which all trades, you want all of that information together. It's difficult. It's an expensive process. It takes a lot of time. It's aggregation, right? So aggregation and joins, when you have to join the information not just from two databases, but also from two different microservices which have their own databases, and they might be storing information there in their own formats. One could be a NoSQL database, the other could be an SQL database. So that's a huge amount of complexity, and you don't want the API gateway to struggle there. So you use something called as an API composer that does the work, all the pre-work of aggregating this information from multiple services and keeping it in sort of a cache, so that you don't have to actually make those joins in real time. All the joins already happened, and API composers do them beforehand and keep the data ready. So API composers are extremely important. Service registries, when you use, you don't just allot one server to one microservice. In the real world, you use containerization, you use container orchestration, and a lot of complex stuff, right? Container orchestration. With each deployment or with any change or any new microservice, the IP addresses keep changing very often. We know that, but the API gateway won't sometimes know. Like many of the times, it won't know which IP address is the latest IP address for which service. So it will make a request to the service registry. There's something called a service registry. The sole job of the service registry is to take into account what is the IP address of which service, and the API gateway just makes a request to the service registry, gets the IP addresses, then calls the relevant microservice and gets the data. Now you might have this question, right? So if you're new to system design, you might have this question that why do I need a separate thing called a service registry? Why do I need something called as gateway? Why do I need API composer? Can't I have just one thing which will have all of this? So the answer is no, because all of these have their own underlying data structures and algorithms. They all work in a different way. They all have their own specialization. They're all different technologies. Like load balancer is a very specialized different technology. API gateway is a very specialized different technology. And you want to have all of these things as separate as possible, because they'll have single responsibility or separation of concern. Even if one thing, even if your API gateway goes down, doesn't mean the load balancer also has to go down, right? So always think in a single responsibility way of thinking. Don't think that you can crowd it together and just again make a big monolith, right? So always think that all these things will be separate. Webhooks. So instead of the way we will be integrating our system with external systems, like in our stock trading platform, the way we'll integrate these systems will be using webhooks instead of just API integrations, because the information in a stock trading platform, it changes very often. You don't want the external systems to keep making requests to you all the time. Okay, you don't want them to make a request, because that's basically constant polling of your APIs, and your system gets overloaded. You don't want that. You want a webhook where whenever we have an update, like here we've taken the example of Stripe, whenever we have an update, we send the update to the external service saying that, hey, now we have an update, and this is the new update, this is what has happened, this is the information that you requested for, you need to subscribe to this information, instead of them calling our API again and again to check for new information. Okay, so this brings in an element of event-drivenness even with our external interactions with external services. So today we'll be learning a lot about event-driven systems, but even before we go into that, I'm just clarifying that even with the external services that we deal with, we will be dealing with them in a very event-driven way. We won't be just having API integrations. Talking about events, you have the standard request-driven architecture where the client makes a request to the server and he gets a response back. So here the client has to wait for a very long period of time, and so this is like synchronous communication, right? You send a request, you wait for a response. Whereas if you want to get asynchronous, you can use event-driven architecture. So synchronous basically is like having a video call with somebody. Asynchronous or having a WhatsApp call with somebody. Asynchronous is like sending him a voice note. So whenever he has time, he can just look at it. Okay. So asynchronous works better for us because it's non-blocking. You don't have to keep waiting for something, and it can happen really fast, and it supports real-time platforms. So what happens is, like, let's say you have a server which has a new event. So like, let's say there's a trade that happened, a buy or sell order that just happened. This event needs to be consumed by different other services to, let's say, send an email or send a notification, all of that stuff. And they can simply respond to those events quickly. They don't have to now, keep waiting, keep calling these APIs. We'll dig into this much deeper on the board that I have for you guys. So even if you just understand that there's a difference, that there's synchronous, asynchronous, and instead of calling APIs, we have something called as events now. So here, like you can see, you have events flowing through a stream, which again we'll discuss in a while. Events happen through two things, queues and streams. So with queues, you get ordered data. So you can keep publishing information in a queue, and then you get all that ordered data. You can keep subscribing to it. And usually we use them with workers. So workers are independent programs, parallel concurrent programs that work from the message queue, and then they do a particular task, a very specific set of tasks, depending on what type of event they received on the event queue. So there could be workers who are listening to a specific event. Whenever they get that event on the event queue, they then execute that particular task. That's how this works, basically. Then you have data streams. Data streams are, they process data in real time. So you have sources and you have producers, consumers. Now you don't need to get into all this in depth, because today we're just talking about very basic stream processing. You don't have to know the underlying concepts of how something like Kafka works. We won't get into that today, but you need to know that data streams basically work in real time. Now, it's okay if this is not very clear to you. All you need to understand right now in this presentation is that data streams work with unordered data, and they work with real-time data processing. And only if this much you've understood, that's okay, because on the board we'll dig down deeper. Producers produce events, consumers consume events. Adapters make sure that the data on the stream is compatible with all the consumers. Brokers basically enable systems to communicate, to exchange information. Like I said, you don't need to understand these. It's completely okay if you don't understand any of this. Just understand data stream has a lot of data flowing through it in real time. Data gets processed in real time. You drive analytics and reports and all of that in real time. We'll dig into that deeper. Now, the big confusion here comes from the fact that if these are streams, what are batches, right? So batches and streams are both going to get used in our system today. So we need to talk about both. Stream processing happens in real time, whereas batch processing happens at a particular time of the day, like 12 p.m. or 1 p.m. or something like that. So with batch processing, you have limited resources. You can use those resources at a particular time of the day to process a lot of information. Stream processing, you can process everything in real time if you have a lot of resources. So like I said, the reason we were learning about streams is because real-time systems, they use streams. So stock trading apps, in our case, they're slightly hybrid. 95% is real-time systems and 5% is request-driven response. So we'll have an element of both in our system design. And real-time systems, especially like stock trading apps, they are near real-time in the sense a few milliseconds of delay is completely okay. They're soft real-time in the sense if the delay increases, it won't hamper anything. It's not mission critical, and it's not at all hard real-time. Now, hard real-time systems are where you send missiles and you have to click on buttons and you send missiles. So they basically, if the delay increases, the system completely fails. So you can't. It's not a hard real-time system. That's to do with embedded systems and hardware and all that stuff. With us in the software world, we work with near real-time system and software systems. Okay. That's about it. Okay, so yeah, last thing I think is Websockets. So we'll be using Websockets to send notifications to the front end. So a lot of people get confused at how does the front end get all those front end or the app or the web app, whatever, how does it get so many notifications or real-time information that's flowing through those graphs? How does it happen? Websockets are very heavily used in stock trading platforms. Instead of making a request and getting a response again and again, what you do is you just make a handshake, WebSocket handshake, and then the web server can keep sending you data one after the other. You don't have to make any request. So it's asynchronously pushing data to you, like all the notifications or the real-time information whenever the web server has any update on the information that you're supposed to see. So that's basically your WebSockets. Now let me, so the first part of the system is over. Okay. How are you liking it, guys? Is it good? Okay. Awesome. Great. So it's going great till now. Okay. Some people are saying it's a bit fast, but we have to do that, guys, because this was the basics of system design. We went through it because like I wanted everybody to be on the same page. That's it.